For centuries, humanity has looked to the sky for answers, building theories, writing equations, and imagining our place in a grand cosmic puzzle. But all of that, our physics, our cosmology, and our understanding of space-time, has now been shaken to its core. What the James Webb Space Telescope has recently observed was never supposed to exist. Galaxies that appear too old, planets that seem impossibly large, structures that are astonishingly perfect, and a signal that is steady, rhythmic, and unlike anything predicted by known astrophysical models. This is not simply another scientific discovery. It is a direct challenge to everything we thought we knew about the universe. The James Webb Space Telescope may have delivered the most profound warning and invitation in human history. If these observations are confirmed, then much of our current understanding of the cosmos may need to be rewritten. During a series of deep-field observations, the James Webb Space Telescope captured some of the most detailed images of the universe ever recorded. But hidden within those breathtaking images was more than beauty. In the galaxy cluster Abell 2744, researchers identified perfectly aligned points of light and remarkably symmetrical structures forming patterns that seemed out of place in the chaotic process of galactic evolution. In the spiral galaxy NGC 1365, unusual patterns of motion suggested gravitational behavior that appeared to contradict our most fundamental models. The surprises did not end there. Similar anomalies began appearing across multiple observations. The farther James Webb looked into the universe, the stranger the cosmos became. Patterns repeated across billions of light years, revealing geometric precision in a universe that was expected to be random. Scientists initially dismissed these findings as coincidence, but the patterns became too frequent and too precise to ignore. Gradually, a new possibility emerged. Perhaps we are not observing randomness at all, but a hidden form of cosmic order that we have yet to understand. Among the many objects studied by the James Webb Space Telescope were the exoplanet HIP 65426b, located hundreds of light-years from Earth. What it revealed left astronomers astonished. This planet is roughly 7 times the mass of Jupiter and orbits its parent star at a distance nearly 3 times greater than Neptune orbits the Sun. Even more surprising, the host star is only about 15 million years old. According to existing theories of planetary formation, a world like this should not exist. There is no visible protoplanetary disk, no remaining material from which such a massive planet could have formed, and no satisfactory explanation for how it could have grown so large, so far from its star, in such a short time while remaining stable. Some researchers have begun considering more unconventional ideas. What if this planet did not originate within its current system? Could it be the remnant of an earlier stellar cycle, a relic somehow transferred, preserved, or deliberately placed? For now, there are no definitive answers. There is only a glowing world, with temperatures exceeding 1,000 degrees, existing in a system that seemingly never had enough time to create it. One of the most extraordinary discoveries made by James Webb was the observation of an Einstein ring, a phenomenon created when the gravity of a massive foreground galaxy bends the light from another galaxy directly behind it. However, the Einstein ring surrounding galaxy J418 is unlike most others ever observed. It forms an almost perfectly complete and uninterrupted circle of light, displaying an astonishing level of mathematical symmetry. Such perfection left even experienced astrophysicists amazed. For an image like this to form, the alignment between the two galaxies must be nearly flawless, accurate to tiny fractions of a degree across billions of light-years. That is not merely rare, it is statistically extraordinary on a cosmic scale. While gravitational lensing itself is well understood, the exceptional precision of this example has raised many more questions than answers. Could it be evidence of a deeper symmetry built into the fabric of space-time itself? Could the universe be governed by an underlying geometry far more ordered than previously imagined? Perhaps no discovery has challenged modern cosmology more than James Webb's observation of massive, fully developed galaxies existing only 180 million years after the supposed Big Bang. Although that span of time sounds immense by human standards, in cosmic history it is astonishingly brief. According to current models, galaxies should not have had enough time to grow to such enormous sizes, organize themselves into spiral structures, or produce the extraordinary brightness that Webb has recorded. Yet these galaxies appear as large and as stable as the Milky Way during an era when the universe should still have consisted primarily of hot gas and scattered matter. These observations have forced cosmologists to reconsider some of their most fundamental assumptions. If these galaxies truly are as old as the data indicates, then our understanding of how the universe formed may be incomplete. The Big Bang, long regarded as a cornerstone of modern cosmology, faces new questions as scientists work to explain observations that existing models struggle to accommodate. Some researchers have even suggested that the universe may possess a far longer and more complex history than previously believed. In a region of space far removed from any major galaxy, the James Webb Space Telescope detected something entirely unexpected, a gravitational lensing effect in an area where no visible object exists. There are no stars, no galaxies, and no black holes, yet the light from much more distant galaxies bends and distorts as though an invisible massive object occupies that region. Astronomers have tentatively attributed this phenomenon to dark matter, the mysterious substance believed to exert gravitational influence despite remaining invisible. However, the strength and precision of the lensing challenge even that explanation. The distortion appears too concentrated and too well-defined to resemble the diffuse distribution normally associated with dark matter. Instead, it behaves more like a distinct object with measurable mass, symmetry, and clear boundaries.